Good morning. Welcome to our webinar, How to Analyze Network Performance Issues from GREYCORTEX. My name is Tony van der Kammen and I will guide you in the next hour through all kinds of performance issues in Ethernet networks, what can happen, and see what you can find in our monitoring system. And so you can resolve the problems. Let's see what kind of problems we can face. Most of the time, there are network outages or people are complaining. The network is slow. The network is slow. Yeah, slow. What is slow? Yeah, the response time is too large, but there are many reasons of that, of course. There could be a lot of retransmissions in the network, and it would be nice when some system take care for counters so that you can see how many retransmissions you have, in what directions, from what sources, from what subnets, to which destinations, that kind of things. Maybe there is some mismatch of quality of service parameters, that you can configure quality of service of DSCP or type of service or all kinds of names for it, but it will serve the same target, and that is priority for certain traffic. Of course, that's only limited in your own network. It's not on the public internet supported, but yeah, we will show you in a minute how it looks like and how you can recognize it if there is a mismatch in configuration. Another part could be, for example, the trace route command. You all know the trace route command on Linux and Windows machines, and what the information it will show. Time to live analytics. You know that there is a counter in the IP world which will lower the time to live each time it will cross a router. So we will talk about it. And when the counter is to 0, what will happen? We will show you in a couple of minutes. Then there are also specific configurations, like you could create port channels, for example, bonding interfaces with a purpose to have a kind of redundancy in your network, or just to expand bandwidth. So you can combine a couple of interfaces together, so you have more throughput port channel. And yeah, the challenge is there. You can make. The next item is, for example, if you have a network in a triangle or with multiple switches, and there is the possibility that you can create loops, of course. You can prevent that, or you can say, yes, I like to create a kind of loops, but only for redundancy reasons. So when one link is broken, that the traffic will follow the other link. Therefore, we can use the STP protocol, the spanning tree protocol. There are several flavors of spanning tree protocol, and we will dig into how to detect what kind of version is configured and what can go wrong. And last but not least, of course, the VLAN mismatch. So if you force traffic into a VLAN, you expect at least that the return traffic will be at the same destination in the same VLAN. But when there are some configuration issues, sometimes you will see it's not in a simple setup, but most of the time in a more complex setup with redundancy and that kind of things, that there is a mismatch. And of course, you can use the spanning tree also over the VLANs. So we will show that in a couple of minutes. At the end, it will all result for a slow network for the end user. But for us as technical guys who needs to maintain the networks, we need to figure out what is slow. Is it the network? Is it the application? Basically, that's where we are going to talk about in the next hour. Let's first see what we can see in the network about the network parameters like round trip time, server response time, out of order messages, retransmissions, user experience time, application response time, that kind of things. So in a simple overview, I try to explain how things are measured. So you can see here how we look as a network monitoring system to the network, and that we are equipped in the network somewhere between the client and the server, and that we are looking at certain signals to measure times. And the times we can measure is the round trip time, for example, server response time, user experience time, delays, jitter. But how to do it? That means that you need to be somewhere in the network, and to see the complete round trip time, like you know in Wireshark, you can also run the round trip time, and you will see there is a part which will measure the time between the Wireshark interface and the server, and a part between the Wireshark interface and the client, and together that's the complete round trip time. What we do is we measure the round trip time in the network, and we can see it between the SYN and the egg, because there you have the complete round trip time. If you measure it between the SYN and the SYN egg, you have the server part, and if you measure it between the SYN egg and the egg, you have the client part. But yeah, in the meantime, we have to see it together. And the positive thing there is, if you measure it this way, it doesn't it doesn't depend on the location where the probe is installed to calculate the round trip time, because it's the total time. Okay, one of the things which is important, we can do that for all TCP messages, because they have sequence numbers and timestamps, so we can measure that there. The next part is, of course, the application response time, server response time, which is measured between server response time is measured between the ACK and the data, which is sent to the client. And if you like to see the application response time, then you have to implement also the client experience. So it's from the request until the data. When the data is coming in packets, then it means there are multiple packets sent, of course. Then we can measure the time between these data packets, and we call that delay. And that delay could be the same every time, but it could be changed because of data has to pass the network, several routers, buffers, whatever, links which are maybe busy and that kind of thing. So there could be, or it's another route which is followed, because it's a dynamically assigned network. So it could be that not all packets do have the same links to get the target, so it could switch, so there could be difference in time intervals, so the delay could be different due to buffers or other things or retransmissions. There could be a difference in delay, and basically the difference in delay, we call it jitter. And this jitter could be equalized by buffers, of course, in routers, or buffers in endpoint applications. Like, you know, if you have a voice phone application on your desktop, there is a jitter buffer inside, and you can adjust that. Most of the time it's automatically arranged, but you can adjust that, and that means that your voice is fluently and not stuttering because of the jitter which is there. I think that voice over IP is most of the sensitive applications for jitter, where you can immediately hear when it's not well configured or when the jitter is too big. So I will get back to that and show you how you can find these kind of things in our Mendel solution. Let's go to the next sheet. And yeah, maybe it's not necessary to explain, but here you can see how it is. So you see the packets there. When there is no jitter, then the delay between the packets is the same, then there is no jitter. When there is a difference between the delay, then we call the difference is the jitter. And of course, what I explained is that jitter buffers are able to equalize the jitter, unless it's not too high, because when it's too high, it doesn't fit in the buffer, and then we will get other problems. We could get out of order packages and even drops, of course, because you see to the right where the packets are sent from a streaming server to a client, that it has to pass, of course, the network. And there are more packets in the network which are going from A to B. So the packet from the streaming server needs to be part of the whole stream of all packets. And that means that routers and switches are busy to handle all these packets. And that means that some packets are stored for a longer time before they are forwarded in a switch or in a router. And that could be the reason that maybe the first packet, and in this example, it's the second packet. You can see the second packet from the streaming server is sent, and it will arrive somewhere on reception level on the third location. So basically, there is a wrong order there. Until then, not a problem, because when the router or the switches in between are able to keep these packets in the buffer and release them in the right order, it's fine. When the buffer is full and there is no space anymore, or it takes too long before the right packet is there, then these packets are dropped. It's an out of order packet, and it could be dropped because it's not in the space, in the limit, in the buffer space to have it in the right order. That means that you are missing packets. When a packet is dropped, then the endpoint will respond on the next packet, which is received, of course, with a message, and that it's good received and the sequence number, and then the server says, okay, you are responding to that packet, but the previous packet I didn't see an acknowledge for that. So yeah, sometimes you need to run a retransmission there. So that's how it works a bit. So take in mind that there's a lot of going on in the configuration of the network, and a lot can go wrong. Most of the time, everything went well, but if there are problems, yeah, we really need to take a look at it. Let's see. Service network outages. What we see at the moment that people are more and more depending on the network, and it should work 24/7, 365 days a year, or 366 days a week. And when there is an outage, then people are a kind of unequipped, so they don't know how to continue because they are missing information. So the network is very, very important, and every outage, minutes of outage, will cost basically money. So it's not good for the business. So we need to prevent it. We can prevent a lot by doing things redundant, but also the mean time to repair needs to be low, and the mean time between failures needs to be as low as possible. And sometimes you have a kind of early indicators, so you can start already actions to prevent and resolve issues. You know, when you have a redundant network and you can see that the traffic is switched to another link, then you should repair the main link and not wait until the second link is down again, because then there is no redundancy anymore. So take action on that. So let's see what we can see on, for example, a high number of retransmissions. Like you all know, for example, in this example, you can see to the left there is data transmitted, and there will with the sequence number, of course, and there is an acknowledge with the same sequence numbers, so the sender knows to send the next data package. Between sending the next data package, or between resending the data and sending the data and receiving the egg, there is a kind of a retransmission timeout. And most people said, yeah, but what is that? So that means when data is sent and the egg is not received within a certain time, that the packet will send again. So it's basically a retransmission. So it's sent with the same sequence number because there was no answer on the first one. But what is the time? Can you tell me exactly what is the time? Is it 5 milliseconds? Is it 1 millisecond? No, you can't tell it what it is. It's calculated dynamically, and it's based on the retransmission timeout. And the retransmission timeout is calculated based on the round trip time. You can imagine when you have a round trip and it will go in your local network, then the round trip time is very low. If you have a round trip to, for example, to the US, from Europe to the US, and that will be a longer, a bigger round trip time. Just in case, for example, the fiber cables are not okay and broken, so you need to go via satellite, for example, then the round trip time will even much longer. And in the meantime, the sender needs to know how long do I need to wait. So for that reason, they use for the retransmission timeout the round trip time. There's a formula for that. I don't like to show everything here because it's too complex, but then you know at least that round trip time, it's not a fixed round trip time. Timeout, retransmission timeout, sorry, is not a fixed timer. So it's calculated based on the round trip time. On the right side, you can see that the answer was not there in time, and the retransmitted packet is there. It could be some reasons, because the packet is robbed or anything like that. If you look at the interface of a router, for example, in the screen you see here is, for example, an interface on the Cisco switch where you can see the drops on an interface. Next part, and that's maybe, I don't know if people are looking at this at the moment, because almost everything is high speed in networks. It's gigabit, it's 10 gig, it's fiber connections, in-home fiber connections. So there is a lot of bandwidth. So sometimes people do forget that there was, in the past, when bandwidth was limited, you have 10 gig half duplex, you have 10 gig full, 10 megabyte per second half duplex, 10 megabyte full duplex, 100 megabits per second full duplex, half duplex. You need to have the quality of the quality of service parameters there. and in the moment it's still there. So everything is backwards compatible. So it's good to have it there. Sometimes you have a lot of bandwidth on your location, but the uplink to the internet is limited. So yeah, you need to handle traffic sometimes in a good way. So there are quality of service parameters defined, and at the moment everybody is talking about DSCP, differentiated service code point. If you look at the table below, you can see that basically there are several names depending on the type of protocol which is used, the packets which are used, but with the same meaning. So you can see the type of service value for interactive video, for example, for high priority is 152, while the DSP value is 38. And the AF abbreviation is AF for force free. Basically, it all means the same, but it's using an other kind of priority parameter in the configuration. It's important, of course, if you configure that you do that consistent in your network. So if you have, for example, traditional voice over IP and you have IP phones, you can have there the specific quality of service parameter for voice over IP. So in this case, if you use the type of service, it's 184. Yeah, you can use that, but you have to be consistent to configure that in every switch router, that this priority is there for that type of service. Again, it's not traveling over the internet, of course. So it's only in your own network you have the chance to put priorities for certain data types. But the important is to make it consistent, because otherwise it doesn't work. At the moment, you also see that voice over IP is just in a specific VLAN, so not interfering with other traffic, and that's how it works. And you can see in operators which are using, for example, VDSL, ADSL, ATM-based, that say, will reserve an ATM path with fixed bandwidth for voice over IP, for example, and that it's flexible. But if you set up a voice call, that at least there is a reservation for bandwidth so that the quality of service is always okay. Quality of service parameters. Let's go to the next item. Network cycling and TTL analytics. So you all know that you can run, or you don't know, I hope you know, at least a trace route on a router, on an endpoint, and it will count the number of hops to reach the target. So I show you below one of the outputs which is there. It's a continuous process. When you start a trace route, it will run it continuously. And if you look at the picture below, I turned on DNS, so just in case the IP addresses do have a DNS name, you can see that there is a DNS name assigned to the router and the next hop. You can see the percentages of loss of data. You can send the number of packages sent. You can see the lowest, the average, and the best response times there, the round trip times for it, and the worst one. And to the right, there is the history. So you can see if there are the green ones are the lowest, the blue ones are a little take a little bit longer. And when it's somewhere red, then you can see that it's broken there. So you can see exactly if you are not able to go, for example, to the Google DNS, and you start a trace route, and the traffic is interrupted here somewhere, and you can see the responses from there, and from then where the interruption is, you don't see any response anymore. Or maybe it's already on your network that the firewall is blocking that kind of traffic, so you can do it. It's a trace route. Another parameter which you can use is, for example, time to live. So that means that it depends on if you have a Windows machine or a Linux machine or whatever. The time to live is basically a counter which is there, and it will be lowered by 1 when it crosses a router. So really when it's crossing a switch, so it needs really to cross a router, and then it will lower the time to live. And why is this mechanism designed? This mechanism is designed when there is no limitation on it, then data packets could get into the internet and end up in a never-ending story. So somewhere there should be an end of the packet, and the time to live counter will lower until it's 0, and then if the packet didn't reach the endpoint before it was 0, the packet will die and will disappear. So it's just to be sure that packets are not traveling for ages and ages in the internet. So there you have the time to live counter. So that's important. There is something I need to tell you about it, because I know that people are running sometimes the trace route and a ping, for example. Let's show you the example I have on my screen. I did a trace route to the Google DNS, and you can see there's a maximum number of hops which were there. So, but at the end, you can see we use nine hops to get to the Google DNS. At the same time, I will run a ping where you can see the time to live, and the time to live. I have a Windows machine, so that means it started with 128, and it's 117. So that means basically 128 minus 117 means that I have 11 hops. And in the trace route, I see only 9. What is the problem? Why is there a difference? This has to do with the mechanism. The mechanism is used for another purpose. So keep that in mind. So the time to live here, it's counted for each session which is sent, for each echo reply is there. And for that reason here, the time to live is 117. And here is the average calculated. So it's another purpose. This is a continuous running command, while this one is every time one command running. So that's the difference. So now you know, if you are going to compare that, there will be always a difference for 2 or 3. So that's the reason for it. So now you know. Let's go to some examples in our GREYCORTEX Mendel solution. Let's go to retransmissions, for example. If you look at our network part, you can see there is analytics. And when you run the analytics, then you can, for example, you can run a filter based on source or destination retransmissions. And here you can find these retransmissions. And of course, we can check what we see: 204, 304 retransmitted packets. Really nice. Let's take a closer look. So we can add this to the filter. We can filter it. Basically, you see the same things now, but now it's for us easier to go to the flows. And we are in the flows. We can take a look at what's going on here. And of course, this is very nice information that you can see that the Samba protocol is used, and you can see source and destination IP addresses. That kind of things were very important. But if we look at the transport layer, and that makes more sense, then we see that the retransmitted packets are 10.38%, and here it's 3.3% of the packets are retransmitted. So you can see at the end the average user experience, the round trip time is there, and the application response time. So this can help you to figure out the retransmissions. And of course, if you like to pinpoint it a little bit more, you can say, okay, is it only from this source to this destination, or is it only from this subnet to that subnet destination? In this case, it's a different subnet, so you could check it, and you could put it in the analytics and say, okay, from this source to that source, and then you can see where really the problems are, where the most retransmissions will start. So one of the things which is helpful to show at least how the retransmissions are seen in our system. If we go to the next one, and that's, for example, the quality of service part, you know, I told you for SIP, it's important that you at least have, not only for SIP, but for the complete voice, at least that you have configured the quality of service well, at least when you have limited bandwidth in your network, that you can have priority when you like to perform a VoIP call from your laptop, from your application somewhere on your phone, or maybe you have a physical appliance in your location. So if we look at the SIP protocol, yeah, except that all the parameters are here, of course. In this case, it's just a registration, which is unauthorized and send again with an unsend. And the second one is authorized, of course. That's how the mechanism works within SIP. But when we look at the link layer protocol, we can see that there are VLAN IDs. So, okay, in this case, there is at least a separate VLAN for the SIP configured. Most of the time that will do the job. But we like to focus on the DSP values, the SCP values, and you can see here that the source is talking AF12, high throughput data. Basically for voice over IP, you should use another one. And on this side, you can see it's even not configured. So yeah, the best way is to have it configured. In this case, it doesn't matter because you saw already that it was a separate VLAN for that. So that means that all the data traffic, streaming traffic, it's not in this VLAN. So this VLAN is dedicated for the SIP services. So that's okay. But otherwise, yeah, you can see if it's configured well here. If you are using the DSCP type of service values in your network at the moment. Let's see what we can discover more. Network performance issues. When I look here, I can see there is an outlier in the subnet for some parameters. What we can do is we can check what is really going on, and just click here, and we can see that if we look here, that normally we have measured for round trip time 5.8 microseconds. And at the moment, we can see that there is measured 899 microseconds. So that means it's 6,500 times more. So that needs some investigation, of course, but yeah, that's how you can see it in the system, of course, that you can see these parameters in the system. So it will warn you when some network performance parameters are just not normal. So they are just increasing or decreasing. And so it means when it's higher or lower, you will get an event for that, an alert for that. And then you can investigate why it's going to happen. Another part where we can look at is for example, the application performance link, performance parameters, sorry. When you look here, yeah, I log in into another system now. You probably see that, and you already see that the color of the GUI has now the day view, so you can switch from day to night. I prefer the night view because I think the dark screen it's better for me. But you can see there is a choice, so it's configurable for each user, and you can see what's going on. So if we look here, there is an application performance outlier. So that means that there is something wrong with the application performance parameters. When we look here, then we can see that the application the response time, when we can see what is measured here, it's 14.7 microseconds, and it's here you can see it's 891. So it's increasing a lot, 16,500 times more. So now you can investigate that kind of things. If you like to know, for example, some parameters for a certain host, for example, that means that also the system will take care for a host for all these kind of parameters. Let's see if I can show you very quickly to show you how it looks like. I'm going to go for a host, for example, and I check here one of the hosts I knew. Then you can see the host parameters are there, and I can show you the view. So you can see for each protocol for this specific host, you can see if he is as a client or he's using it as a local or remote, of course. There you can see all the numbers which are there. So you can see the packets in, out, round trip time, server response time, all these kind of parameters are there, and they are in a nice overview. So you can see it for each host separately. Good. Next one, time to live. We are going for a time to live. So what you can see here is I did go to the analytics and I created a filter with the time to live values there. And you can see that we can see the source time to live and the destination time to live. And of course, the destination time to live will go down when the destination is there over more hubs, right? So if you have more hubs, then the counter is lower, lower, lower. What you like to know is basically when the counter is 0. So what you can do is you can create a filter here and say, for example, the DST, TL, TT, right, I need to, DST, TT, the minimum time to live destination is smaller than, take 15, for example. Let's save it and let's search it. And you will see that a lot of destinations are unreachable because at the end, the destination time to live is 0. So that are things you can do with the analytics part. You are able to create all kinds of attributes there. Sorry, you can create all kinds of attributes. You can search for all kinds of metrics, and you can then put order by, and on top of that you can create an additional filter, and of course you can rank it like you want, and drill down, put it to the filter, and do your analytics. Service unavailable. Let's see what we can see. What will happen when the service is unavailable? When you look in the system, you will get an alert that the service is unavailable. So you can see in this case, it's a mail server, which is unavailable. And more important is here at the end, you can see the number of source hosts, destination host, and the number of events. So I have 3 events that the service is not available, and I got that message because this destination host was not available for 3 source hosts. Important is that you see these counters and that you know what it means. So it means 3 hosts are connecting to this destination host and the service was unavailable. So that sounds okay. Maybe only 3 hosts are using the service on that host. That's fine. But here you can see, is it a service outage or is it a network outage? When it's a network outage, you can see here multiple hosts, source hosts, and multiple destinations which are not reachable. Then you will have a network outage. When it's 1 service or 2 services down, you can see in the destination host only 2, and the source host, it depends on how many people are using that kind of application. So it really makes sense to see it here and to analyze what's going on. Let's go to the next part in our presentation, and that is services and network outages, but on layer 2. Everybody knows when link 1 is missing, when you don't have any physical or wireless connection, then no communication, that's obvious, but also the layer 2 needs to be there configured, and there are a lot of things are going on layer 2. In the IT world, most of the time layer 2 is just part of the communication, because most of the communication is on layer 3 or higher. But we have also not only IT, but we have also OT environments, of course. And there are a lot of OT protocols which are only using the layer 2 configuration. And the communication is on layer 2 based on MAC addresses. So it's very important that we understand a bit about how things are working on the layer 2. I like to pinpoint only a couple of examples here, because it's not a training, so I only like to show you what's going on. We talked about port channels to have redundancy between switches, routers, whatever. and use port channels for that. Or maybe you like to increase bandwidth between switches. For example, you have switches with only 1 gig ports and you like to connect these switches to each other, but the traffic which needs to travel between the switches is more or less 1 gig. So you can create port channels with multiple 1 gig links added together. So then it's more to expand bandwidth, of course. That means there's a ether type for it. It's called LACP, and it's a special code for that, so that we know in the MAC frame, in the layer 2 frame, what is the meaning of it. So you can see here for LACP the number 34 825 is used. That's common agreed, you know. So when I can show you that there is a standardization organization, the IANA, and there is some part in them which is the IEEE, which will go for these kind of numbers. So if you go to look for the, let's see, it was 34.825, then you can see here it's used for slow protocols, link aggregation, right? So basically all these numbers, and you can see here the decimal and the hex number 8809. So if we go back here, you can see the 8809. So that's based on the ether type for the complete MAC frame. If I look at the MAC addresses, also there are some meanings. Like, you know, you have multicast, you have broadcast, and you have also specific protocols to use for us. So if I can show you what, for example, that the zero, what these MAC addresses do mean, then you can see here that it's a protocol. The 02 is the protocol for slow multicast protocols, for example. You can see there are all kinds of standardization and reserved type of MAC addresses which are used to configure and to run right on your network. So it would be nice when we could monitor these kinds of things and if it's right configured. Let's go back to where we were. So port channels is one of the things which is running on layer 2, of course. You can configure it as in different modes. You can turn it on both sides and it will work until one of the locations is down, then it's not working anymore. So most of the time people will use the active configuration. So that means it will dynamically assign it to each other, and when one of the link is down, it will route the traffic automatically or send the traffic automatically over the other link. So you can use, the most safe way is to use active, and then you can use on the other side the passive, or you can use active. So both is good. Passive, it's not an option, and the combination with on active, that's also not an option. So it's active, passive, or on. So it's what you want. Take in mind what is going to happen if it's not going to work. Is your traffic dropped? Is it sent to the other link? So it's very important that you configure it in the right way. Most of the time, automatically, it's well configured, but it could be a problem if somebody thinks, yeah, I'm going to change it, and he doesn't know the impact, and until one of the links is gone, and then it seems that the traffic is on a dead end and not rerouted again. The second part where we can look at is the spanning tree protocol. Yeah, most of the people will know what spanning tree does mean. It means if you have for example, a setup which is redundant. So that means if you have, in this example, we have 3 switches. Yeah, I think spanning tree is running on layer 2, of course. So you have 3 switches. That means if the traffic will go from the switch, distributed switch 1 to the core, it's fine. It's going to work because there is a link. If this link is broken, you like to have the traffic automatically rerouted via the distri 2 to the core router because there is an alternative link. That's really nice, but you like to prevent that there are, for example, during a broadcast that packets are running in circles, you know. So basically, if they are going to run in circles, you will occupy all the bandwidth, and at the end, it's not possible anymore to run your regular traffic because of the broadcast storm which is there, because it's running in circles. And for that reason, if you have this kind of redundant solution, you need to have a protocol which prevents that broadcast storms can start, right? So that means the protocol to use for that is spanning tree, and that means that we also have MAC addresses for that we can use for the spanning tree, and that means that these MAC addresses will end at CD at the end. That means that this is assigned for the STP protocol. So it's also one of the MAC addresses which is fixed assigned, so you know when it's there, then it's used for the STP protocol. STP will work with bridge protocol data units, so that means they are always sent over all the links, but they prevent to get the regular data to run over all the links. So it can only run where the port is open for STP. So basically that's how it works. There are several flavors for that because, you know, they started with STP as a great solution, and then there was a kind of a rapid STP, so it was RSTP, and then you have also the VLANs over STP, and then you have the multi STP was there. So that means several flavors with several purposes, right? In this example, I show also a specific MAC address for CDP, Cisco Discovery Protocol, to discover neighbors, right? Spanning tree protocol, yeah, I already told you, CD is the MAC address for that. Ethernet type, Ether type is 8192, and yeah, we have to take care that there is the right, if you are using STP also on VLANs, that it's right configured so that there is no VLAN mismatch for that. The IEEE has also a recommendation for VLANs. When you look at Cisco in the past, the very past, they had ISL for VLANs, but at the moment everybody is using the .1Q and the VLAN tagging, which is standard by the IEEE, and it's using the Ether type 33024. Okay, and the regular multicast MAC address is ending at 0. So basically that's the information which I like to give you, and I have a couple of examples where I can show you this information in the Mendel. Layer 2 communication. So let's start and see what we can see here. We see there is a detection of unrecognized layer 2 communication. And I just showed you, for example, that the 34825 was there for LACP. and that communication is there. So this is how you can recognize if LACP is running on your network, and where it's running. So you will see that port number there, but you see also other port numbers, and yeah, not everything is always right, but sometimes it's good that you can look in these other port numbers which are used. Let's take the 205, for example, and show you what we can see here. So basically what we can get out of it, this is more the CDP, the Cisco Discovery Protocol, where you can see at the end that it's a Cisco switch, 24 ports, and we are on the gigabit 1024. So at least there is some information available, not everything, but okay, you can see it in the Mendel for that. Let's go to another example. When we look to STP protocols, you can see that the VLAN standard STP protocol is there, or the multi STP protocol is there. Let's show one of the links where we can see the number of ports. Yeah, in this case, what you use, you can see that it's layer 2 communication because there are no IP addresses assigned. So that's obvious. When we look at MAC addresses, you can see that CDP is used here because the MAC address is ending on CC here, right? The icon which is there, it's not here. You can see it's a Cisco icon, so it's using the CDP discovery protocol to find what is on the other end. At the moment, it's not clear what it does see. If I go to the next, you see there is also a regular broadcast sent over the layer 2 link. It's 00 at the end, so it's okay. When I go further, then you can see here that CD is sent. So it's also STP protocol is sent to that location. And when we go further, then you can see suddenly that the Cisco Discovery Protocol discovered that it was a Cisco switch, right? And you can see also the port number which is used for that. So it's the rapid STP here. So when I go and switch to the mstp, then you can see that you have here the 3324, 33024, which is the VLAN tagging, which is the ether type, which is there. And you can see that there is a multicast sent, a regular multicast sent on the 00, based on the VLAN tagging. VLAN at the moment it's 0 because it's sent in that VLAN port. So that means when you look at the link itself, you could see the VLAN IDs, but when it's sent in a VLAN, then you don't see the traffic inside of that. There's no VLAN in VLAN, it's only a VLAN and the traffic inside. So basically that's the information you can see there. Let's go to the last example. And that's, for example, the VLAN mismatch. So if we look at our analytics screen again, then we can search for source subnets, destination subnets, destination VLAN, source VLANs, and we can check if there is some mismatch. Of course, you can go over it, and it could be all kinds of reasons, you know. There could be a reason that you are using a part of Wi-Fi with roaming and something is misconfigured. If you go over the list, of course, then you can see sometimes it's a little bit strange. So you can see here the source VLAN is 318 and 2003, and the return is 2003. Okay, that's nice, but why the 313 is there? And yeah, so it seems to work this way, the source to the destination and the return to here, so that's okay. The other way around, here it's a 601 sending to 600. There is no match there, so then we have the challenge to figure out what is going wrong there, and we can use the Mendel for that to see where is the mismatch and between which subnets it's starting, and for that you can use the Mendel to analyze it and to drill down and see where it starts and what kinds of sessions are going right and what is wrong. And then you can figure out how the route is configured. When I look at the time, then the hour is there. So that means that we are at the end of the webinar. I really like to thank you for your attention. We will go over the questions we have, and we will send the answers in the update by email. Thanks for watching, and see you next time. Bye bye.